Hello and welcome to Notes for Section 7.7, page 9 of your Unit 7 notes packet. Today we're going to talk about an angle of elevation. Imagine that you're outside and you're standing on the ground. Wonderful. Now, some distance in front of you, there's something, let's say it's a flagpole. Easy enough to imagine. We're going to talk about an angle of elevation and an angle of depression. Today, specifically, we talk about the angle of elevation. If you're just looking horizontal, your eye line straight forward, your head is not tilted at all. That would be horizontal at 0 degrees. An angle of elevation would be if you need to tilt your head upward to maybe look at something. So you can't actually see the top of the flagpole unless you tilt your head just a little bit. This is an angle of elevation. The key word here is elevation. We're talking about above. And our reference for above or below is going to be horizontal. So basically think about your eye line. If you have to tilt your head upward, you're looking at an angle of elevation. And if you tilt your head downward, you're looking at an angle of depression. So we start out with the angle of elevation specifically. This is our introduction to word problems. So when we talk about an angle of elevation, we're going to make sure that when we're drawing our triangles, we're labeling each of those parts specifically. We're looking for an angle that would be above the horizontal line in a right triangle. So let's think about what might be involved here when it comes to actually applying a word problem with trigonometry. First of all, your number one step, you need to draw a picture. The first part of any word problem is actually breaking it down, understanding it, and making sure that you know what pieces make up all the parts of that puzzle. I know that it might take a little bit of time, but it's easier to draw a picture and make sure you know what's going on than to just try to guess and hope that you drew the picture correctly. So in our first example, we have a bird sitting in a tree. Okay, I'm going to use the margin here to draw my picture, and then I'll draw another triangle. So here's my tree. It's lovely. It looks great. I'm going to try to draw a bird. It's going to look great. Just know that it is a bird. Okay? There you go. It's up in the tree. It has a beak. There you go. The next thing that I'm told is that this tree is a certain height. So I know that this tree is 250 feet tall. That's a very, very tall tree. Okay, so when I'm thinking about my picture, I need to make sure that from the bottom to the actual bird, I can see that that label has to be 250 feet. I'll remind myself of the labels of the units in a minute. The next part of this says that you are viewing the bird from a 10-degree angle of elevation. So the first thing I'm going to do is actually draw myself. If I'm looking at the bird, I'm probably not going to be that close to the actual tree, so I'm going to draw myself at a distance. I don't know how far, so I'm just going to guess. The next thing that I think about is my actual eye line. So if I was looking straight at a 250-foot tall tree, I would not be able to see this bird. That means that I have to tilt my head upward just a little bit to be able to actually see the bird in the tree. 10 degrees is what I'm told is that actual angle of elevation. So it makes sense that in my picture, I've labeled the theta where it is. The next thing that I have to do is ask myself, what is the problem looking for? And it says, how far away are you from the tree? So how many feet am I standing from this actual 250-foot tall tree if I have to make a 10-degree angle of elevation with the horizontal? After I've actually drawn the picture, this is where I'm going to go through and I'm going to treat it like a regular trigonometry. You have a picture, you can turn this into a right triangle. I know that the tree is 250 feet tall. I know that I'm looking for my horizontal distance, and I know that I'm dealing with a 10-degree angle. So if I draw this triangle, and I'm not sure why I drew it so small, but it'll work. If I draw this triangle, I can basically see the word problem broken down without all of the extra picture part. No tree, no person, no bird. That means that I'm ready to label each of the parts of the right triangle. I have the hypotenuse, the opposite, the adjacent, and then our angle of reference, theta. I like to start with the hypotenuse because it's always going to be the side length that is opposite the right angle. In this case, I don't actually know anything about the length of that side. So I go ahead and I look at theta, which is a 10-degree angle. To identify the opposite and the adjacent, I look at the two side lengths that make the actual angle of reference, and x is my adjacent side. That means that the 250 feet, that has to be the opposite side because it's the only other side length I haven't labeled, and it's the one that's on the opposite side of the triangle. So I want to solve for the adjacent side, and I have the length of the opposite side. That's going to lead me to picking the trig function tangent. Here I have that the tangent of theta is equal to the opposite side over the adjacent side. What I need to do now is replace all of the pieces of information I do know. I know that the angle of reference is 10, so I want the tangent of 10 degrees. I also know that the opposite side and the adjacent side are my right-hand side of the equal sign. 250 is the opposite side, and x is the adjacent side. My goal here is to solve for x, so I want to get the x by itself, which means that I'm going to use algebra, multiplication and division, to get the x so that I can solve for it algebraically. First, I need to get the x out of the denominator of that fraction, so I multiply by x on both sides, and I end up with x being multiplied by the tangent of 10, and that's going to get me to the side length 250 feet. That means that what I need to do is one more step here. I don't quite have the x by itself, but it's really, really close. So I'm going to divide by the tangent of 10 on both sides. I have to do this because I have to get the x by itself. It might not feel like algebra, but that's all you're doing here is just the steps of algebra. It's just going to be multiplication and division though. That means that what I'm ready to do is get my calculator out. And in the calculator, I'm going to do 250 divided by the tangent of 10. Make sure that your calculator is in degrees. Degrees, that's something that you want to check. And then make sure that you're looking at what the directions tell you to do. If it's a side length, you're going to be rounding to the nearest tenth. If it's an angle measure, you're going to be rounding to the nearest whole number. So just read the directions and see what they tell you about rounding. And if you're not sure, you can always ask. This particular problem has us round to the nearest tenth, so I'm going to round to 1 decimal place. In my calculator, I'm ready to put 250 divided by tangent of 10, change that from radians to degrees, and then once I do this, I want to make sure, I'm going to go ahead and close the parentheses. It doesn't really change my answer, but I just want to make sure. I end up with 1,417.82 feet, but my direction stayed around to the nearest tenth. So I'm going to make that 1,417.8 feet. And that's how far you'd have to be standing from that 250-foot tall tree if you were to see that bird by raising your head 10 degrees above the horizontal. Angle of elevation, problem number 1. Exciting stuff, manageable. You can do it. So let's look at another example. Not every single example is going to look exactly the same, and you're going to have to make sure that when you're drawing your picture and you're interpreting the question that you're reading it really carefully. Sometimes you'll be solving for a side length, and sometimes you'll be solving for an angle measure. In this particular question, we have Mary, okay? I'm going to start by drawing Mary. Hello. It says here, it should say that Mary flies a kite, but it says that Mary flies kite, okay? So I'm going to go ahead and then I'm going to draw a kite. That's going to go up in the air. Usually it's that little diamond looking shape. It really is called a kite though. The next piece of information I'm told is that this kite has a string that has a length of 45 feet. That means that there is absolutely no world that the kite can get more than 45 feet away from Mary. That's a length that I need to write down, and that's going to be the length that I write here diagonally. Basically, the exact distance from Mary to the base of the kite. Now, when you fly a kite, it doesn't fly straight up in the air and it doesn't fly straight horizontally because you have wind. So, we're told here that the kite is 32 feet in the air. And that means that even though we're 45 feet away from the kite, it's still 32 feet in the air. The question then is to find the angle of elevation if Mary is 5 feet tall. And you have to think about why that might be important, okay? So Mary obviously has to raise her head above the horizontal to see the actual kite. So when I think about her height, I have to include that in the 32-foot measurement. 32 feet is how high the actual kite is off the ground, or is actually off the ground. However, Mary is a 5-foot height. So if you take that extra 5 feet out, that's really the distance that you're talking about, the kite being from Mary's hand, let's say. But we're going to factor that in a little bit later. In my picture, I want to determine what that actual angle of elevation is. So if I'm looking above the horizontal, I've just highlighted that in pink, and I've labeled that with my theta. At this point, we've drawn a wonderful picture. You can kind of see what's going on. And so now we would try to label our hypotenuse, our opposite, our adjacent, and our theta. The first thing I'm going to write down is the length of the actual kite string, which is 45 feet. The next piece of information that I'm looking at is going to be based on height, because I don't have a distance. I guess I'm not looking for the distance. I don't have a distance. If the actual kite is 32 feet in the air and Mary is 5 feet off the ground, when she holds the kite, it's safe to say that really the kite is only 27 feet. The kite is removed 27 feet from Mary's hand. So the actual height is 27 feet. And if that doesn't make sense, make sure to ask me about it. And that means that the actual height, the distance from the horizontal or the vertical distance from Mary's hand to the base of the kite is 27 feet instead of 32. So when I label my triangle, I don't actually use the number 32, I use 27 instead. Let's start by labeling the hypotenuse, which is the length of that 45-foot kite string. The next thing that I do is I look at my angle of reference, theta, and in this case, my angle of reference is made by two side lengths. One of them is the hypotenuse, and the other one is the adjacent. I don't actually know anything about the adjacent side, and I don't have a whole lot of room to show that, but I'm just going to draw a line through that. I don't know anything about the adjacent side. That means I have one side length left, and that's going to be the opposite side. The opposite side length is that actual height, the distance vertically from Mary's hand to the base of the kite. And since that's the opposite side, and I have the length of the hypotenuse, this is going to allow me to pick a trig function. I don't know anything about the adjacent side, so I have to use sine. The formula for sine is that the sine of theta is the same as the opposite over the hypotenuse. So I go ahead and replace everything that I can. The theta stays where it is, but I've just color-coded it now. And then I have opposite over hypotenuse. In this case, what needs to happen is I replace the opposite with 27, and then I replace the hypotenuse with 45. So right now, I know that the sine of theta has to be exactly equal to the fraction 27 over 45. That doesn't really help me a whole lot though. So what I want to do instead is I want to take the inverse sine of both sides of the equation. That means I have the inverse sine of the sine of theta, and then I have the inverse sine of the fraction 27 over 45. This is what goes into the calculator. If you're looking at these fractions and you notice that they can be simplified, you are more than welcome to simplify the fraction, but the calculator is smart enough to handle that. You really don't need to simplify the fraction. If I take the inverse sine of sine, that gives me the theta by itself. And then on the right-hand side, I have to do the inverse sine of 27 divided by 45. So this is where the calculator comes in handy. And I can make sure that my calculator is in degrees, yes, but I also want to make sure that I use the right trig function. Because in the last problem, I used tangent, but here I'm using an inverse trig function. So I want to make sure that in the calculator I pick the right function. For the inverse sine, I'm looking for an exponent of -1. So inverse sine of 27 over 45. The directions here tell me to round to the nearest whole degree, which means that I have 36.869. That's pretty clearly going to round me all the way up to the next number, which is a 37-degree angle. And now you've seen an angle of elevation problem where you solve for a side length, and you've seen an angle of elevation problem where you solve for an angle of elevation in degrees. I hope this was helpful, and if not, make sure that you're reaching out with any questions or concerns.